There is a particular kind of quiet that only happens late. Not since exactly. There's still the soft tick of something cooling down somewhere in the house. Still the faint suggestion of wind outside doing nothing dramatic, just moving. And in that kind of quiet, if you let your mind go just slightly loose, numbers start behaving strangely. They stop being counts of things. They start being something else, something that resists being held. That's where this starts, not with a telescope, not with Andromeda, just with the specific, slightly uncomfortable feeling of a number that won't fit. 2.5 million. Say it slowly. 2.5 million light years. Now, and this is worth doing, just once, try to feel it. Not calculate it. Not convert it into kilometers or miles or any unit that would only make things worse. Just try to hold 2.5 million light years the way you'd hold a stone in your palm. Test its weight. You can't. That's not a personal failure. That's just the shape of human cognition bumping against something it was never built to carry. Our minds evolved to track predators across a savanna, to judge whether a river was crossable, to remember which berries were which. We got very good at distances up to maybe a few days of walking. After that, the machinery starts to strain. After that, numbers exist on a kind of scoreboard, bigger than the last one, smaller than the next, but they stop meaning anything the way small numbers mean things. 2.5 million light years means the light now arriving at your eye left its source before your species existed, before Homo sapiens existed, before, arguably, anything you'd recognize as human had yet assembled itself on this planet. That light has been travelling since before we had language to describe travelling. Here is what 2.5 million light years is not. It is not a long drive. It is not a long flight. It is not even a long life, multiplied over and over. Those comparisons, the ones you sometimes see where someone helpfully converts cosmic distances into something relatable like, it would take this many lifetimes end to end, those comparisons are well-intentioned, and they don't work. Not really. What they do is make the number feel more manageable, which is exactly the wrong direction. Because the truth of this distance is that it stops being a distance at some point. It becomes a different category of thing entirely. It becomes closer to a wall than a road. A wall without a door. That's, well, we'll get to that. On a clear night, far enough from city lights, you can see Andromeda with your naked eye. This is the part that gets me, honestly. That's the part I keep coming back to and finding slightly hazy. I want to say unsettling, though that's not quite the right word either. Strange, quietly strange, because there it is, a faint smear of light, hovering just off the constellation Perseus. If you know where to look, barely more than a thumbprint of glow against the dark. Easy to mistake for a cloud, easy to miss entirely if you're not patient. And it is 2.5 million light years away. You're looking at it with the same eyes that learn to read faces, to judge ripeness in fruit, to find shapes in shadows. Those eyes, these stubbornly biological instruments, are receiving photons that have crossed 2.5 million years of empty space to land on your retina. And your brain, doing what brains do, converts it into a mild visual impression. Oh, faint blur noted, moving on. There's a gap there, between what is happening physically and what the mind registers. And that gap is, in a way, the whole problem this video is about. If this kind of quiet science helps you rest, consider supporting the work on Patreon. The link is in the description. This is a self-funded project, and every bit of support keeps it going. Andromeda is not the farthest thing you can see, not even close. On exceptional nights, with patience and good conditions, the human eye can detect the Triangulum Galaxy, slightly farther, fainter, more elusive, and the universe itself extends for tens of billions of light years in every direction, populated with hundreds of billions of galaxies we can observe only because their light happened to be travelling in our direction long enough to arrive. But Andromeda is the closest major one, the nearest large galaxy, our nearest neighbour in the cosmic sense, which is a bit like saying the nearest other continent is your neighbour if the continents were separated by an ocean made entirely of nothing, and your fastest boat moved at a crawl that would take longer than Earth has existed to reach the other shore. 2.5 million light years, nearest neighbour. The universe has a particular kind of humour about proximity. A light year is the distance light covers in 1 year. Light moves at roughly 300,000 kilometres per second, fast enough to circle the Earth more than 7 times in a single second. In a year, it covers about 9.46 trillion kilometres. So a light year is not a unit of time, even though the word year is sitting right there in it, creating reasonable confusion. It's a unit of distance, a very large one. And 2.5 million of them it's a lot. That sounds inadequate. It is inadequate. But sometimes the low-resolution version is the honest one. It's a lot in the way that very, very cold is technically accurate for absolute zero. Correct, insufficient. The number just sits there, daring you to really look at it. The central thing this chapter is trying to settle around, and I think it's worth being direct about it just once, is the difference between seeing something and being able to reach it. These are not the same, not in the ordinary world, but especially not here. When you see a mountain from a window, there is at least the theoretical possibility of walking to it. Time would be required. Effort. But the path exists. The terrain connects you to the thing you're seeing. The act of looking and the act of reaching belong to the same category of possible experience. Andromeda is not like that. The light that lets you see it is real. The photons landed. Something happened in your eye that was caused by something that happened in that galaxy 2.5 million years ago. In that narrow sense, there is a physical connection, ancient, stretched, impossibly thin, but real. The possibility of going there, though, that belongs to a completely different conversation, a much harder conversation, one that requires not just asking how fast we can go or how long we could survive the journey, but whether the structure of space-time itself permits what we're imagining. And that answer, as it turns out, is complicated in a way that is, well, it is not the answer you'd expect. So stay with the faint blur for a moment. The smudge of ancient light. It has been travelling since before your species learned to stand upright, and it crossed that distance, all of it, at the fastest speed anything in the universe is permitted to move, and it still needed 2.5 million years to get here. Whatever the chapter ahead is building toward, it begins here, with the weight of a number that won't behave, with light that left before we existed, with the strange, grounded, mildly vertiginous feeling of looking at something real that is, in almost every meaningful sense, unreachable. That feeling is not a problem to be solved tonight. It's just the beginning of the question. Voyager 1 is still out there. That sentence deserves a moment. Not analysis, just a moment. Because it's one of those facts that sounds triumphant when you first hear it, and then slowly, if you sit with it long enough, starts to feel like something else entirely. We launched it in 1977. It's been moving every second since. It is the farthest human-made object in existence, which is a genuine achievement, the kind that belongs in the same drawer as fire and writing, and the first time someone thought to put a wheel on something heavy. Voyager 1 represents, in some very real sense, the longest reach humanity has ever made, and it is nowhere. Not nowhere as an insult, nowhere as a description. Voyager 1 is currently somewhere in interstellar space, past the heliopause, past the region where the sun's influence over local particles starts to lose the argument. It is beyond our solar system. That alone would have seemed impossible to someone standing on the Earth 500 years ago. The idea that we'd send something past the edge of what the sun controls and it would keep going, still talking to us, still sending back readings on magnetic fields and particle densities in the space between stars. It travels at roughly 17 kilometers per second. 17 kilometers per second sounds fast. It is fast. Faster than almost anything a human body has ever experienced. Faster than most things we have names for in everyday life. But speed, like distance, has a way of becoming meaningless when the scale shifts far enough. At 17 kilometers per second, Voyager 1 would need approximately 73,000 years to reach the nearest star. Not the nearest galaxy, the nearest star. Proxima Centauri, 4.2 light-years away, 73,000 years. Agriculture is about 12,000 years old, written language somewhere around 5,000. The entire span of recorded human civilization and every kingdom, every war, every invention, every name we remember fits inside roughly 5,000 years with some room to spare. 73,000 years is not a travel time. It's a geological event. It's the kind of duration during which coastlines move, species diverge, and whatever version of humanity boards the hypothetical ship would not be recognizably related to whoever waved goodbye at launch. And that's for the nearest star. Andromeda is not a star. Andromeda is 2.5 million light-years away, which means at Voyager's pace the journey would take something in the range of 45 billion years. The universe itself is only 13.8 billion years old. So we're talking about a trip that, at our current best speed, would take more than 3 times the age of everything that exists. There is no meaningful way to dress that up. I keep coming back to Voyager specifically, not because it's the only example, but because there's something almost stubbornly honest about it. It doesn't pretend. Parker Solar Probe moves faster during its closest approaches to the Sun, reaching speeds above 600,000 kilometers per hour in the grip of solar gravity. But that speed is borrowed. Pull it away from the Sun's influence and it slows. It's not carrying that speed anywhere useful. Voyager earned its velocity differently. A gravitational slingshot from Jupiter, then Saturn, using the planet's own motion to whip the probe faster, the way a ball thrown against a moving wall comes back harder than it left. It's elegant, actually, old-fashioned in a way. The kind of engineering that uses what's already there rather than carrying fuel for every inch of the journey. But elegant or not, 17 kilometers per second is what we got. And 17 kilometers per second, applied to intergalactic distances, is, the word I want is negligible, but even that feels generous. It's like measuring the depth of an ocean with a thread. There's a coffee mug on my desk that I've had so long the logo on it has mostly worn away. I mention this only because I was staring at it while thinking through this chapter, and there's something about objects that outlast their own legibility that felt relevant, though I couldn't tell you exactly how. Maybe it's just that Voyager is also, in some sense, an object outlasting the context in which it was made. The engineers who built it are old now, or gone. The culture that launched it has changed in ways they couldn't have predicted. And the probe keeps moving, indifferent to all of that, 17 kilometers per second, in a direction that will never arrive anywhere we were trying to go. The honest version of the speed problem is this: we are not slow because we haven't tried hard enough. We are slow because chemical propulsion, the burning of fuel to generate thrust, has a ceiling. A stubborn, unbudging ceiling built into the physics of the method itself. The more fuel you carry, the heavier the craft. The more fuel you need to move the heavier craft, the heavier that makes the craft. It's a loop that tightens quickly. Rockets are fighting this with every launch, and they are winning just enough to reach orbit, just enough to send small probes to distant planets, just enough to call it spaceflight without embarrassment. But just enough to reach orbit, and fast enough for intergalactic travel, are not on the same map. Ion drives are better in some ways, more efficient, capable of building speed slowly over long periods. Nuclear thermal propulsion has been studied, proposed, partially developed. Laser-propelled light sails have been seriously suggested for reaching Proxima Centauri within a human lifetime, but we're talking about gram-scale probes, not ships, not passengers. Even the most optimistic of these concepts, the ones that feel almost reckless in their ambition, top out at maybe 10 or 20% of the speed of light. At 10% of light speed, Andromeda is still 25 million years away. There's no bridge being built here. That's the thing. This isn't like the history of aviation, where the Wright brothers flew for 12 seconds in 1903 and 66 years later, someone walked on the moon. That was fast, yes, but it was all happening within the same physical framework. Thrust, lift, controlled combustion, incremental engineering. The jump from Kitty Hawk to Apollo was enormous in ambition and achievement, but it didn't require the laws of physics to behave differently. Reaching Andromeda, reaching it within anything resembling a human timescale, doesn't just require better engineering. It requires something that conventional propulsion, no matter how refined, structurally cannot provide. Speed as a solution runs out long before the destination appears, which is where things get strange. Or not strange exactly, that's the wrong word. Where things get honest about what the problem actually is, because the limit isn't just fuel efficiency or material science, or the difficulty of surviving a long journey. The limit is baked into the geometry of space and the behavior of light. The fastest speed anything with mass can achieve is the speed of light, and even that is not really achievable, only approachable. As you push toward it, the energy required to accelerate further increases without end. The last few % of light speed would require more energy than we can meaningfully describe, and light speed itself, applied to Andromeda, still means 2.5 million years. Faster than light is not simply an engineering problem. It is a statement that under the rules currently understood to govern the universe, cannot mean what we want it to mean without something more fundamental changing. What that something might be, whether it exists, whether it's even physically coherent, is the slow, difficult question that starts in the next part of this. For now, Voyager keeps moving, 17 kilometers per second, into the space between stars, which is also, incidentally, nowhere near Andromeda, not even pointed in the right direction as it happens. Moving away from the Sun in the rough direction of the constellation of Fucus, faithfully transmitting data about a region of space no probe has ever visited before, doing exactly what it was built to do, just not this. Start with your heartbeat. Not metaphorically, actually. There it is, that low, steady, slightly wet percussion happening in your chest right now, whether you're thinking about it or not. It's been doing this since before you were born, will do it until it stops, and this is the part worth sitting with. It is a clock, a biological one, imprecise and variable and influenced by temperature and fear, and whether you had coffee too late, but a clock nonetheless. Something in your body measuring out time in beats, the way a metronome measures out music in ticks. Now, what if running made it slow down, not from exhaustion, not because you're out of breath, but because the act of moving through space at high enough speed actually, physically, genuinely altered the rate at which time moved inside your body, inside every process, every chemical reaction, every firing neuron, every heartbeat relative to someone standing still? That's not a thought experiment. That's what happens. Time dilation is one of those physics facts that sounds made up every single time you encounter it, no matter how many times you've heard it before. I've read about it dozens of times, and it still lands with this faint, uncooperative thud, the feeling of a thing that should be wrong but isn't. The universe, it turns out, does not treat time as a fixed backdrop against which events unfold. Time is not the stage. Time is part of the performance. It bends, it stretches, it moves at different rates depending on how fast you're moving and how deep you are in a gravitational field. And both of those effects are real, measured, confirmed, not by exotic experiments in distant laboratories, but by the GPS satellites above your head right now, which have to correct for relativistic time shifts daily, or their positioning would drift into uselessness within hours. So, time dilation is not theoretical in the sense of being untested. It is theoretical in the sense of being very, very strange. Here is what it actually does to a traveller, applied to something like Andromeda. You're on a ship. The ship accelerates, not instantly, not dramatically, but steadily, building toward a speed that is almost the speed of light. Not quite, almost. At 99% of light speed, something quiet happens to time. For every year that passes aboard the ship, roughly 7 years pass outside it. At 99.9%, that ratio becomes closer to 22 to 1, pushed to 99.99%, and it becomes a number that requires you to reconsider what you thought a year meant. At sufficiently extreme speeds, a traveller could, in principle, cross millions of light years while aging only decades. The physics is clear on this. The math works. The universe apparently permits it. This is the part where most explanations pause to let you feel hopeful. Don't feel too hopeful, because here is the part that arrives just after the hopeful part. Quiet and a little cold, like opening a window in a warm room. While you are crossing those millions of light years and aging only decades, the universe outside is not waiting. It is not paused. It is moving at its own rate, the rate of someone standing still watching you disappear into the distance, and by the time you arrive anywhere, millions of years have elapsed out there. Not for you, for everything else. You step off the ship. You're 40 years older than when you boarded. The universe is 2.5 million years older. Earth, if it still exists, if the sun has not yet expanded into a red giant and swallowed it, is 2.5 million years further along. Whatever civilization launched you is gone, replaced by something unrecognizable, or nothing at all. The people who wave goodbye are not just dead, they are archaeological. This is, I think, the part of time dilation that the word dilation does not prepare you for. It sounds expansive. Dilation sounds like opening, like something getting larger and more accommodating. What it actually is, applied to this situation, is something closer to a severing. There's a moment, I remember reading about this, sitting in a chair that was slightly too cold because the heating in the building had gone off for the night and I hadn't noticed until my hands started feeling stiff, where the physicist's framing and the human framing of this fact come completely apart from each other. The physicist's framing is, relativistic time dilation means that a traveller moving at near light speed experiences less proper time than a stationary observer. This is correct, experimentally verified and consistent with special relativity. The human framing is, you get there, but everything you were going back to is gone. Both are true. They don't contradict each other. They are just describing the same mathematics from two positions that feel nothing alike. No, perhaps severing isn't quite it either. Let me try again. It's more like the journey is real, The arrival is real, but the return address stops existing somewhere en route. Time dilation doesn't take anything from you in the way loss usually works. You don't feel it. Your heartbeat doesn't stutter. The clocks aboard the ship tick at a perfectly normal rate from your perspective. Every second feels like a second. Every meal takes the time a meal takes. Sleep arrives when it arrives. There is no sensation of time compressing. There is just you aging normally, crossing an abnormal distance while outside the ship windows the universe quietly runs through millions of years of its own business. It's a one-way accommodation. The universe will let you cross the distance. It just won't let you go home afterward. Not to anything you'd recognize. This makes time dilation a very specific kind of loophole. Generous in one direction, completely indifferent in every other. You can use it. You can, in principle, use it to reach Andromeda within a human lifetime. And this is not science fiction. This is the actual implication of the physics, however staggeringly far we are from the engineering required to make it real. The physics does not forbid it. It just means you arrive alone. In a galaxy you don't know. In a universe that has aged past anything familiar. With no signal delay long enough to matter, because there's no one left to signal. Time dilation is, and I feel mildly irrational saying this, but here it is, generous in a way that somehow makes things worse. Like a door that opens but only goes one direction. Like a gift that arrives slightly too late to be useful. The universe offers this strange, lopsided mercy, and the mercy is real, and the mercy is useless for any purpose we'd actually have. And this is before we even address the engineering. Accelerating a ship, not a probe, not a gram-scale solar sail, but a thing large enough to carry a human being with air and water, and the basic machinery of biological survival, to 99% of light speed, requires energy on a scale that makes every power source humanity has ever built look like a match held up to measure a room. The fuel mass problem is brutal. You need fuel to accelerate the fuel, and the ratio collapses quickly into something impractical. Theoretical drives using antimatter annihilation or laser propulsion could in principle close some of that gap, but even antimatter, the most energy-dense stuff we know how to describe, remains essentially impossible to produce or store at the quantities needed. And the radiation. Moving through interstellar space at near light speed, even the sparse hydrogen atoms scattered through the void, 1 per cubic centimetre on average, which sounds like almost nothing, become a grinding, relentless particle bombardment. The shielding required would add mass. The mass would require more energy. The energy would require more fuel. It loops, tightening each time, so the physics permits it. Loosely, distantly, in the way that physics permits lots of things it has no obligation to make easy. The clock keeps ticking. Your clock, specifically the one in your chest, the one that has been running this whole time without being asked to. At rest, it runs at the rate the universe allows for a body at rest. No dilation, no compression, just time moving the way time moves for everything that isn't hurtling through space at a substantial fraction of light speed, which, tonight, is you. And that turns out to be a much harder problem than it first appeared, because if getting to Andromeda requires either millions of years of conventional travel or the sundering sacrifice of near light speed dilation, then maybe the question isn't really about going faster at all. Maybe the question is about whether space itself can be made to cooperate. That's a different kind of question, older in some ways, stranger in almost every way, and it begins not with speed but with shape. There is something almost embarrassing about how long it takes to notice that space has a shape. Not the space in a room, not the space between furniture, but space itself. The medium through which light moves and matter drifts and time, as it turns out, does things nobody fully anticipated until someone sat down with the right equations and let them say what they wanted to say. Space has geometry. It curves. It responds to mass the way the surface of a heavy mattress responds to something placed on it. Slowly, completely, without resistance. The whole structure reorganizing itself around the weight it's been given. This is not analogy. This is, as best as physics currently understands, what is actually happening. Mass tells space how to bend. Space tells mass how to move. And between those two instructions, everything that has ever fallen, orbited, or drifted in the history of the universe has been following a script written in the language of geometry. The embarrassing part is that this was always true, long before anyone described it. The planets were curving through warped space-time billions of years before Newton gave us a formula for the force they seemed to be obeying, and billions of years before Einstein replaced that formula with a deeper picture in which the force was never really a force at all, just geometry, doing what geometry does. Take a piece of paper, flat, ordinary, the kind that picks up the smell of whatever room it's been sitting in, slightly stale if it's been in a drawer, faintly sharp if it's near a window. Draw 2 points on it, one near each edge, as far apart as the width of the page allows. The straight line distance between them is fixed. You can measure it. If you are an ant living on the surface of that paper, moving only along the surface, that distance would be the minimum journey, the most efficient path, the baseline from which all other routes are longer. Now fold the paper. Bring the 2 points close together, close enough that they nearly touch and hold them there. The straight line distance hasn't changed. It's still the width of an unfolded page. But the points are, in this moment, almost adjacent. An ant that could step through the paper, not along the surface but through the fold itself, would cross in almost no distance at all. This is the image, not a perfect one, not a complete one, but the image that sits underneath everything that follows, so it's worth letting it settle before it gets complicated. The complication begins almost immediately, because the paper analogy works as an image, but misleads as a description, and the place where it misleads is important. When we fold paper, we fold it through a third dimension. The paper bends into the space above and below it, and the shortcut exists because we moved through that external space. When physicists talk about space-time curvature and the possibility of connected regions, there is no agreed external dimension that space-time bends into, no higher-up space through which a shortcut passes. The curvature is intrinsic. It's a property of the geometry itself, not a folding into something else. The mathematics captures this. The intuition does what intuition does with general relativity, which is approximately nothing useful. So the folded paper is a gesture toward the idea, not a map of it. Hold it loosely. In 1935, Albert Einstein and Nathan Rosen published a paper that was not about wormholes. This is worth saying clearly, because the history gets compressed in retellings and the compression changes the feel of it. They were working on a problem in quantum mechanics, trying to understand whether the singular point at the center of a black hole, the place where the equations break down entirely and the mathematics produces infinities that physics doesn't know how to handle, could be replaced by something more geometrically continuous. They were looking for a way to describe particles without points. What they found, working through the structure of the Schwarzschild solution to Einstein's field equations, was that a black hole's geometry, taken seriously, extended fully, didn't terminate at a singularity. It connected. It emerged, mathematically, into another region of space-time, a bridge, two mouths joined by a throat, each mouth looking like a black hole from the outside, the whole structure existing as a solution to equations that had been written down 20 years earlier, without anyone noticing this was inside them. They called it a bridge. Other people later called it other things. The name that stuck, Wormhole, came from John Wheeler in the 1950s, which is a slightly odd provenance for one of the most evocative terms in theoretical physics. But here we are. What Einstein and Rosen found was not a door. That's the correction worth making quietly and without drama. The structure they described, the original Einstein-Rosen bridge, is not traversable. It exists in the mathematics of an eternal, non-rotating black hole, and it exists only instantaneously, in a technical sense. The throat pinches off so rapidly that nothing, not even light, could pass through before the connection closes. It is a bridge in the same way that a photograph of a bridge is a bridge. The structure is real. The crossing is not available. This matters because a lot of what gets discussed enthusiastically about wormholes, the shortcuts, the intergalactic travel, the folded paper shortcut made physical, does not come from Einstein and Rosen's 1935 paper. It comes from what happened later, when other physicists looked at the bridge and asked a different question. Not does this exist, but could a version of this be made to stay open? That is a much harder question with a much more demanding answer, and it arrives in a different chapter. For now, the geometry. Space-time, the unified fabric of three spatial dimensions and one time dimension that general relativity describes, is not rigid. It is, for want of a less undignified word, pliable. Not soft, not weak, but responsive in a way that rigid things are not. Mass warps it. Energy warps it. Motion through it is affected by its shape in ways that feel like forces, but are, at bottom, the straightest possible paths through curved terrain. A planet orbiting a star is not being pulled in a circle. It is following the most geometrically natural path through a region of spacetime that the star's mass has already bent into a curve. The reason this matters for wormholes is that if spacetime can be curved by mass and energy, which it demonstrably can, which we have measured, which is confirmed every time a GPS satellite adjusts its clock, then the question of whether it can be curved in more dramatic ways, in ways that produce connected regions far from each other in ordinary terms, is at least a geometrically coherent question. The equations of general relativity don't forbid it, they contain it. Solutions that describe connected regions exist within the mathematics of the theory. The same theory that describes Mercury's orbit and gravitational waves and the bending of light around the sun. Whether the universe builds such things, or whether building them is something that could in principle be done, or whether the conditions required make the whole project physically incoherent, that is where the geometry stops being helpful and the material requirements begin. It seems worth pausing here, in the middle of all this spatial geometry, to note something that sits slightly outside it. The reason any of this feels hopeful, the reason the wormhole idea has the emotional weight it does, the reason it gets returned to again and again in both physics papers and science fiction, is not really about Andromeda, not specifically. It is about a much older and more stubborn human discomfort with limits. The universe is very large. We are very slow. The gap between those two facts is, under conventional physics, permanent and absolute. And something in the pattern of human thought resists permanent and absolute in a way that keeps generating new questions, keeps probing the edges of what the equations allow, keeps looking for the fold in the paper. Whether that instinct will ever find something real on the other side of it, whether the geometry permits not just the mathematics of a connection, but an actual physical traversable one, is a question that begins with what you would need to put inside the throat to keep it from closing. And what you would need is, well, it is the kind of thing that makes the geometry seem like the easy part. The throat closes. This is the first thing to understand, and it arrives not as a dramatic event but as a quiet default. The thing the geometry does when left alone, the thing space-time prefers in the absence of anything telling it otherwise. A wormhole throat, in every solution that general relativity produces without additional ingredients, does not stay open. It pinches. It collapses inward on itself with a speed that makes the word instant feel sluggish. Faster than light could cross it, faster than any signal could make it through, faster than the structure can be useful for anything at all. It opens in the mathematical sense, and then it is gone, in every sense that matters. This is not a flaw in the theory, it is what the theory predicts. The geometry, left to its own devices, finds stability and closure. Think about what it would take to hold a door open against something that wanted very badly to shut. Not a door on a hinge with a string you could wedge a shoe against. Something more like a tunnel through rock that is actively trying to compress. The walls pressing from every direction at once, the ceiling and floor and sides all moving inward with the patient, indifferent force of geology. To keep that tunnel open, you would need something inside it exerting an outward pressure, something that pushed back, something whose entire physical character was defined by its refusal to let the walls meet. That is approximately the situation at the throat of a traversable wormhole. Approximately. The actual mechanics are more subtle and stranger than any tunnel analogy can carry, but the core requirement is structurally similar. To hold the throat open, something must be present that pushes outward against the gravitational tendency to close. And not just any something. The something must have properties that ordinary matter, every atom of every element in the periodic table, every particle we have ever detected or inferred or described with any confidence, does not possess. The name for what is needed is exotic matter. It's a placeholder name, really. The kind of label physicists use when they need to call something something before they know what it is. What it describes is not a specific substance. It describes a set of required properties, and the most important of those properties is this: negative energy density. This is not the same as low energy, not the same as cold or inert or dim. Negative energy density means something more disturbing than any of those. It means matter whose energy contribution to a region of space is, in the accounting the universe keeps, below zero, less than nothing. Matter that, and this is where the phrasing always gets a bit strained, because English was not built for this, matter that does not attract but repels. Not in the way a charged particle repels another of the same charge, which is a force acting between things, more fundamentally than that. A repulsion built into the geometry itself, a pushing outward written into the curvature of the space around the material. Ordinary matter does not do this, not even close. Exotic matter is not dark matter, which is a common conflation worth clearing away. Dark matter is mysterious, yes, undetected directly, inferred from its gravitational effects on galaxies, unknown in composition, but it behaves gravitationally like ordinary matter. It attracts, it clusters, it pulls. Whatever dark matter is, it is not doing the thing exotic matter would need to do. The two are sometimes mentioned in the same breath because they are both unknown, both named with slightly dramatic adjectives, both sitting at the edges of what we've confirmed. But the resemblance ends at the naming. Dark matter, as far as anyone can tell, would be useless at a wormhole throat. What is needed is something that, in the full machinery of the general relativity's energy conditions, violates those conditions. Specifically the null energy condition, a statement in normal circumstances that the energy density measured by any observer moving at any speed through any region of space will never be negative. Exotic matter violates this. It is defined by the violation. Here is the hesitation. There is a quantum effect, real, measured, uncontested, called the Casimir effect, in which two uncharged metal plates placed very close together in a vacuum experience an attractive force. This force arises because the space between the plates excludes certain wavelengths of quantum vacuum fluctuations, while the space outside admits them freely, creating a measurable pressure difference. And the energy of the vacuum between the plates, in the accounting relevant to this discussion, is negative. Negative, real, confirmed in experiments that any well-equipped laboratory can reproduce. This is sometimes presented as evidence that exotic matter is possible, that the universe already contains regions of negative energy density, that the Casimir effect demonstrates the principle at work. And in a narrow technical sense, this is not wrong. The negative energy exists. The effect is real. The problem, the quiet deflating problem debate, is a scale. The Casimir effect produces negative energy densities that are almost incomprehensibly small, relevant only across distances measured in nanometers, requiring geometry so precise and conditions so controlled that nothing remotely like it exists in nature without deliberate engineering. The amount of negative energy needed to hold a wormhole throat open, one large enough for anything material to pass through, is, according to calculations that have been refined over decades, so vastly larger than what the Casimir effect provides that the comparison barely constitutes a comparison at all. It is a bit like noting that a candle flame proves fire exists, and then using that to argue that the sun could have been lit with a match. The Casimir effect hints it does not supply. There is something almost ornery about the wormhole throat, considered as a physical object, not dangerous, not malevolent, and just deeply constitutionally uncooperative. Every approach to keeping it open runs into the same wall. The quantities involved are beyond reach. The materials required may not exist, and the framework in which the solution is being sought, classical general relativity, has its own opinions about energy conditions that make the requirements even stricter than they might otherwise be. Some researchers have explored whether modified theories of gravity might relax these requirements, whether certain configurations of quantum fields might supply what classical matter cannot, whether the constraints derived from the null energy condition might be loosened by effects that only become relevant at scales where quantum gravity, a theory we do not yet fully have, would apply. These are genuine research directions, published in journals, taken seriously by physicists who have spent careers on the relevant mathematics. None of them have produced a wormhole throat that stays open. None of them have confirmed that exotic matter, in the sense required, exists anywhere in the universe. Outside there is rain starting, or that's what it sounds like, the first light scatter of drops on a surface somewhere. The kind of sound that arrives before you've decided whether it's rain or something else. It registers and then recedes, the way background sounds do when attention is elsewhere. The wormhole throat recedes the same way, in a sense. You can approach it theoretically. You can describe what it would need. You can spend serious scientific time on the question of what might hold it and how, and then the specific unyielding answer arrives. Nothing we know of. Nothing we have found. Nothing the universe has yet offered up for inspection that could do what the throat requires, which leaves the question exactly where it has been since Kip Thorne first wrote it down, precisely in 1988. Open in the theoretical sense, unanswered in the physical one. The door as designed needs something to hold it. What that something is, whether it can exist, whether it already exists somewhere we haven't looked, whether the entire framework needs revision before the question can even be asked properly, is a problem that remains, with quiet stubbornness, unsolved. And unsolved is not the same as impossible. It just means the next part of the story hasn't been written yet. Carl Sagan had a problem. He was writing a novel, Contact as it would eventually be called, and he needed his protagonist to travel to the star Vega, 25 light years away. He had already decided she would make the journey, had already built the story around the fact of it, but he wanted the mechanism to be something a physicist wouldn't wince at, something with enough structural plausibility that it should sit on the page without embarrassing anyone who knew the relevant equations. He'd been working with wormholes as the device, the way science fiction writers often do, loosely, intuitively, reaching for the concept without worrying too much about the scaffolding underneath. But Sagan was not a careless person. He sent a draft to Kip Thorne. This was 1985. Thorne was already a significant figure in theoretical physics, a relativist, a specialist in the mathematical behavior of extreme gravitational systems, the kind of physicist whose relationship with general relativity was, by that point, measured in decades of close attention. He read the draft. He noticed that Sagan's wormhole, as written, wouldn't quite work. The mechanism had the protagonist falling into a black hole, which in reality would not deliver her to Vega, but would instead compress her into something that no longer had opinions about where it was going. Thorne suggested a different structure, something that stayed open, something without an event horizon, and then, being the kind of person who cannot look at an interesting physics problem without wanting to know what's actually inside it, he started working out whether such a thing was mathematically coherent. That shift from "this story needs a plausible device" to "wait, is this actually possible?" is the moment worth pausing at. Not because it's dramatic, it isn't particularly. It's a phone call or a letter or whatever, the 1985 version of a colleague saying, let me think about that looked like. But the consequence of it was that Thorne, with his graduate student Michael Morris, spent time building a mathematical description of a traversable wormhole from scratch, not assuming one existed, not borrowing loosely from the Einstein-Rosen bridge, but constructing a metric, a formal geometric description of a spacetime that connected two distant regions through a throat that remained open and stable, with no event horizon and no singularity, allowing passage in both directions. The paper they published in 1988 was titled, with a certain deliberate understatement, "Wormholes in Space-Time and Their Use for Interstellar Travel, a Tool for Teaching General Relativity." The subtitle is, I find this genuinely charming in a slightly dry way, almost aggressively modest, a tool for teaching, as though the whole exercise was pedagogical, as though they hadn't just written down the first mathematically rigorous description of a structure that, if it existed, would change everything about what movement through the universe meant. What the Morris-Thorne paper actually did was clarify the question. Before it, wormholes were a loose concept, present in the solutions to Einstein's equations, yes, but understood primarily as non-traversable, as mathematical curiosities that didn't connect to any physically achievable situation. The Einstein-Rosen bridge was the canonical version, and the canonical version collapsed before anything could cross it. Morris and Thorne asked a different question. They didn't ask whether wormholes existed. They asked, if we require that a wormhole be traversable, that it stay open, that a human could pass through it without being destroyed by tidal forces, that the journey take a reasonable amount of time, what conditions does the space-time geometry have to satisfy? What does the math demand? And then they work backward from those requirements to find what kind of matter would have to be present at the throat to produce the necessary geometry. The answer was exotic matter, specifically matter with negative energy density. The same requirement we arrived at in the last part of this, from a different direction. Morris and Thorne didn't discover this arbitrarily. They derived it from the geometry up. If you want traversability, the equations tell you what you need. And what you need is something the universe has not yet produced on demand. This is the part where the story stops being about Sagan and becomes something more stubborn. Because the Morris-Thorne wormhole is not a proof of possibility, this is the correction worth making gently, without deflating what is genuinely interesting about the paper. What Morris and Thorne showed is that general relativity does not prohibit traversable wormholes. The equations contain them. A space-time with a stable open throat is a mathematically consistent solution to Einstein's field equations. What they did not show, what they were careful not to claim, is that such a wormhole could be built, or that exotic matter exists, or that the structure they described corresponds to anything the physical universe actually produces. The paper is a map of what would have to be true, not a report of something found. Thorne has been consistent about this over the years. The work was genuine physics, and he has always treated it as such, as an honest exploration of what general relativity permits, conducted rigorously enough that its conclusions could be trusted within the framework of the theory. But the gap between permitted by the equations and achievable in practice is, in this case, enormous, and not yet bridged by anything except mathematics. The research that went into understanding this, the actual papers, the derivations, the arguments physicists have been making and refining for decades about energy conditions and throat stability and the minimum requirements for traversability, is dense in the way that papers written for other physicists tend to be dense. If you want to sit with the primary sources, the detailed notes from the research behind this video are available over on Patreon. The link is in the description. This is a self-funded project, and having that kind of support there makes it possible to keep going deeper into this material rather than staying at the surface of it. What Sagan did with the physics, in the end, is interesting in its own right. Contact the novel, and the film that followed, and also treats the wormhole with a seriousness that most science fiction doesn't bother with. The machine built to access it is enormous, precise, requiring materials and energy that strain the civilization constructing it. The journey when it happens is disorienting in ways that feel physically motivated rather than dramatically convenient. Sagan used Thorne's framework not as a magic door, but as a thing with weight and consequence and cost. And then, of course, Ellie Arroway arrives. She travels, she sees what she sees. She comes back with no external evidence, only her own account of something that cannot be verified by anyone who wasn't there. I've thought about that ending more than once while working on this, not because it's a metaphor for anything specific, but because there's something in it that feels honest about the nature of the wormhole question more broadly. The physics permits a structure. The structure, if it existed, would allow a crossing. The crossing would arrive you somewhere real, somewhere with its own physics and light and observable facts. And then, and this is the part that doesn't resolve, there is still the question of whether anyone would believe you. Morris went on to other work. Thorne continued in gravitational physics for decades, contributing to the theoretical foundations that eventually helped LIGO detect gravitational waves, a separate achievement, enormous in its own right, that has nothing to do with wormholes and everything to do with what happens when you take general relativity seriously enough to build instruments that can hear it. Sagan finished the novel. It was published in 1985. He died in 1996, before the film adaptation was released, before gravitational wave detection, before a lot of things, though knowing him from his writing, he would probably have found something to be delighted about in all of it. The wormhole question he prompted, the one Thorne and Morris formalised, is still open, still being worked on, still generating papers that push at the energy conditions, that explore modified gravity theories, that ask whether quantum effects might supply what classical matter refuses to provide. It started because a novelist wanted his physics to be honest. That's not nothing. It might even be, though I'm aware this is the kind of observation that sounds better late at night than it does in the morning, it might be exactly the right origin story for a question this large. Andromeda is coming. Not quickly by any standard that maps onto lived experience. 250,000 miles per hour sounds fast until you place it against the distance it has to cover, and then it settles into something closer to geological. Patient. The kind of motion you'd miss if you only looked twice in a lifetime or a century or 1,000 years. It has been approaching for longer than the Earth has had a complex life on it, and it will continue approaching for longer than human civilization has existed, multiplied many times over before anything dramatic occurs. But it is coming. The blue shift in its spectrum is unambiguous. The light arriving from Andromeda is compressed, its wavelengths shortened by the motion of the source toward the receiver, and that compression is a measurement, not an interpretation. Andromeda is not drifting. It is falling in the technical sense toward the Milky Way, pulled by the combined gravitational mass of both galaxies and the dark matter halos that surround them, vast and invisible, and apparently very committed to this particular outcome. The word collision is the one that gets used, and it is accurate enough while also being, the right word here is misleading or maybe just incomplete. A galactic collision is not a collision in the way two cars collide, or two stones, or any two objects whose bulk determines what happens when they meet. Galaxies are not solid, they are not even close to solid, they are mostly empty space punctuated by stars. And stars are themselves mostly empty space punctuated by dense hot plasma, and the distances between stars, even in the crowded central regions of a galaxy, are so ragged and vast that when two galaxies pass through each other, the probability of any two individual stars making direct contact is, by calculation, negligibly close to zero. What happens instead is gravitational. The galaxies distort each other. Tidal forces pull streamers of stars out of their original orbits, flinging some into new trajectories, pulling others into elongated arcs that trail behind the moving galactic cores like something being slowly unravelled, which is not quite right either, but is closer than most comparisons. The gas clouds compress where the galaxies overlap, triggering bursts of new star formation, lighting up regions that were previously quiet. The central supermassive black holes, one in each galaxy, spiral gradually toward each other over millions of years, eventually merging in an event that would release gravitational waves detectable in principle across enormous distances. The stars themselves mostly survive, they just end up somewhere different. For a long time, the timing on all of this was understood to be approximately 4 billion years from now. First close approach, then a long gravitational dance, then full merger into a single elliptical galaxy, somewhere around 6 billion years out. This was the number that NASA published, the one derived from Hubble Space Telescope measurements of Andromeda's motion, the one that made it into every article about the collision written between roughly 2012 and 2024. It was a confident number, well-sourced. Based on precise measurements of Andromeda's position over years, tracking the proper motion, the sideways drift across the sky, with the kind of patience that only becomes available when you have a space telescope pointed steadily at the same object across a long baseline of time. Then the Gaia spacecraft accumulated data. Gaia, the European Space Agency's mission to map the positions and motions of over 1 billion stars with extraordinary precision produced measurements that made the earlier Hubble data look not wrong exactly, but incomplete. And in 2025, a paper published in Nature Astronomy by Tilsawala and colleagues fed the new Gaia data, combined with updated mass estimates for the Milky Way, Andromeda, and the other significant members of the local group, into 100,000 simulated futures of the local group's gravitational evolution. The results were not what the confident number had suggested. In roughly half of the simulations, the Milky Way and Andromeda do collide, eventually over billions of years, through a process of gravitational friction and orbital decay. In the other half, they don't. They pass close, they distort each other, and then they separate, moving into a gradual orbital relationship that never produces a merger. And when the gravitational influence of the Large Magellanic Cloud, a satellite galaxy of the Milky Way, large enough to have its own significant gravitational pull, is properly included, the probability of a direct head-on collision drops further, around 2% in some of the scenarios. 2%. This is not the number that had been in circulation. The reason the Large Magellanic Cloud matters is interesting in its own slightly awkward way. Its orbital path around the Milky Way runs roughly perpendicular to the plane of the Milky Way Andromeda approach, which means its gravitational tug on the Milky Way is not aligned with the direction Andromeda is coming from. It nudges, it defects, it introduces a wobble into the Milky Way's trajectory that, accumulated over billions of years of orbital mechanics, is enough to shift the outcome of the eventual encounter in ways that earlier models didn't fully account for. Gravity, in this situation, is performing a kind of stubborn arithmetic, adding together the pulls of every significant mass in the local group and producing an answer that is, apparently, less certain than it looked a decade ago. There's a specific feeling that comes with sitting in a chair late enough that the room has gone properly dark except for one light, working through a problem that keeps producing new qualifications. The Andromeda collision is one of those problems. Every time a number settles, something arrives to unsettle it, not to disprove it, but to add uncertainty in the way that more careful measurement tends to add uncertainty rather than remove it. The 2012 result wasn't wrong. The 2025 result isn't the final word either. It is the current best approximation of a deeply complicated gravitational future, and it will probably be refined again. What it does, practically speaking, is loosen the narrative. The collision was always far enough away to be abstract. 4 billion years is not a number that changes behavior, not a deadline that reorganizes priorities, but it was at least a definite event on a long calendar. Now it is a maybe. A probable close approach, a possible merger, a gravitational story whose ending depends on variables that were, until recently, not being measured with enough precision to matter. There is a quiet irony available here, though it doesn't need to be pressed too hard. The question this video is organized around, whether a wormhole is the only way to reach Andromeda and why that way remains closed, assumes Andromeda is a stable destination, a fixed point, something that will be there to arrive at if the physics of arrival were ever figured out. The 2025 data introduces a different wrinkle. Not just that we cannot reach Andromeda, but that Andromeda itself, as a distinct galaxy, as a separate structure with its own identity and boundaries, may not remain what it currently is for the relevant timescales. If it merges with the Milky Way in 4 billion years, it becomes something else, part of a new, combined elliptical system. Its stars redistributed into new orbits, its structure dissolved into a larger whole. And if it doesn't merge, if the Large Magellanic Cloud's intervention nudges the trajectories enough that the two galaxies only pass and drift, then Andromeda will eventually recede. The universe is expanding. The local group is gravitationally bound, which is why Andromeda approaches at all, why the expansion of space doesn't carry it away from us the way it carries everything outside the local group. But in the very long run, even gravitationally bound systems have limits. The destination, in other words, is not necessarily permanent. Whether this changes anything about the physics of wormholes and exotic matter, and the requirements of traversability, it doesn't, not directly. The distance is what it is, the equations are what they are. It just adds a certain texture to the problem. The sort of texture that arrives when a question you can't answer is also, it turns out, aimed at a target that isn't standing still. The kettle on the stove takes about 4 minutes to boil. This is not a remarkable observation. It happens millions of times a day all over the world in kitchens that smell like last night's cooking and morning coffee. And nobody thinks twice about it because the energy required is small, available, and domesticated. Extracted from a grid that hums along invisibly, fed by fuel or wind or falling water, arriving at the element in the kettle as something utterly ordinary. 4 minutes, a small amount of electricity, hot water. The reason to start there is that energy, as a concept, only becomes legible when it has a scale, and the scale relevant to wormholes, to the exotic matter requirements, to the propulsion requirements, to any physical mechanism that might actually bridge 2.5 million light years, is so far removed from the kettle that the kettle becomes the only honest starting point. You have to begin somewhere recognizable before the numbers stop meaning anything at all. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a way of classifying civilizations by their energy use, not by their culture, their technology, their philosophy, or any of the qualities that tend to dominate how civilizations assess themselves. Just energy. How much of it they can access, store, and direct. A Type 1 civilization uses all the energy available on its home planet, the full output of sunlight hitting the surface, geothermal energy, every source that the planet itself provides or receives. Earth is not yet a Type 1 civilization. We are somewhere around 0.73 on the scale, a number that sounds almost respectable until you register what it means. We are using a fraction of the energy available to us on a single planet, and we are calling that our current technological ceiling. A Type 2 civilization harnesses the full energy output of its star. All of it, every photon directed and used. The Sun puts out approximately 3.8 times 10 to the 26th power watts. That number has enough zeros that writing it out produces something that looks typographical rather than numerical. A Type 3 civilization commands the energy output of its entire galaxy. Hundreds of billions of stars, their combined luminosity captured and applied. This is, and the understatement here is intentional, a lot. The Kardashev scale is not a prediction. It is not a roadmap or a promise. It is a measuring tool, and like all measuring tools, it is most useful when it stops being abstract and starts being applied to a specific problem. The specific problem here is this. The proposals that exist for bridging distances like the one between us and Andromeda, wormholes, warp drives, any mechanism that manipulates send-time geometry rather than simply accelerating through it, all require, in the calculations that have been done, energies that are not Type 1 or Type 2 problems. They are Type 3 problems. They require the kind of energy that would only be available to a civilization that has already solved every other energy problem it has ever faced, at every scale, across an entire galaxy. This is not said to be discouraging. It is said because accuracy matters more than comfort, and because the scale of the requirement is itself informative. It tells you something about what kind of problem this actually is. Not an engineering problem in the ordinary sense, not a matter of better materials or more efficient propulsion systems or incremental improvement on what we already have. Something more fundamental, something that sits outside the range of what can be approached gradually. The light barrier is the underlying reason. Special relativity, Einstein's 1905 framework for understanding motion, time, and the relationship between them, contains a limit that is, in the most literal physical sense, unbudging. Nothing with mass can reach the speed of light. Not because of any specific obstacle in the way, not because we haven't built an engine capable of it, but because the mathematics of relativistic mass makes it structurally impossible. As an object with mass accelerates toward light speed, the energy required to accelerate it further increases, not linearly, not even exponentially in the ordinary sense, but in a way that approaches infinity as the speed approaches c. The last fraction of a percent of light speed would require more energy than exists in any finite system. The light barrier is, I want to say stubborn, but that implies it's resisting something. It isn't resisting. It's simply the shape of the relationship between mass, velocity, and energy at relativistic scales. It doesn't push back. It just sits there. A fixed feature of how the universe is structured, indifferent to how much you want to cross it. So conventional propulsion, however refined, however advanced, hits this wall. Not a wall it can wear down or tunnel through with better engineering. A wall that is the same wall regardless of the engineering. The reason wormholes enter the conversation, the reason they are treated as theoretically serious rather than simply fantastic, is that they represent a category of solution that doesn't try to cross the light barrier at all. A traversable wormhole doesn't move anything faster than light. It connects two distant points in space-time so that the distance between them, measured through the wormhole, is much smaller than the distance measured through ordinary space. The traveller moves at perfectly normal speeds, well below light speed, and still arrives somewhere that would have taken millions of years to reach by any conventional path. This is the distinction that makes wormholes interesting to physicists, rather than just to science fiction writers. They are in principle relativity compatible. They don't ask for the impossible in the way that faster-than-light travel through ordinary space asks for the impossible. They ask for something different, something arguably stranger, certainly harder to produce, but not prohibited by special relativity in the blunt way that superluminal propulsion is prohibited. What they ask for instead is energy and material conditions that belong to the Kardashev Type 3 range. The exotic matter required to hold a wormhole throat open, in the quantities that calculations suggest would be needed for a throat large enough to be useful, represents an energy budget that would strain even the most generous reading of what an advanced civilization might eventually command. Type 3 is not, it should be said, a description of what any civilization has achieved. It is a category that exists as a theoretical maximum, the upper end of what Kardashev's framework could describe for a civilization operating within a single galaxy. Whether any civilization anywhere has reached it is unknown. Whether it is reachable at all, whether the path from Type 0 to Type 3 is a natural progression that intelligence tends towards, or whether it is blocked by physics or extinction or choices we can't currently anticipate, is also unknown. What it is in this context is a measure of distance, not spatial distance, but the distance between where we are and where we would need to be for the wormhole solution to Andromeda to become an engineering problem rather than a physics fantasy. That distance is, if anything, more difficult to conceptualize than the 2.5 million light-years it would help us cross. There is something almost clarifying about this, if you let it settle rather than immediately looking for a way around it. The problem of reaching Andromeda is not a problem that technology, applied incrementally to current physics, can solve. It is not a matter of building bigger rockets or more efficient drives or better shielding against cosmic radiation. Those improvements matter for other problems, for reaching Mars, for reaching nearby stars in the very long run, for the gradual expansion of human presence within the solar system and perhaps, eventually, the nearest stellar neighborhood. They are real and worth pursuing. But Andromeda is different in kind, not just in degree. The gap between what conventional physics permits and what reaching Andromeda requires is not a gap that closes with effort applied along the current trajectory. It requires either a fundamentally different relationship with space-time, the kind that wormholes represent in theory, or timescales that exceed the lifespan of anything we would recognize as human civilization by many orders of magnitude. The kettle boils in 4 minutes. That energy, scaled up by every factor of improvement we can reasonably imagine across the next century, barely registers against what the equations require. Which is not despair, it is just the shape of the problem held clearly, without softening the edges to make it more comfortable to look at. The shape is what it is, and knowing the shape precisely is, at minimum, more useful than not knowing it. There is a number less than 0. This should not be surprising. Mathematics has had negative numbers for centuries, and they cause no particular distress when they appear on a bank statement or a thermometer, or the elevation reading of a valley floor. Below 0 is a well-behaved concept. It has a clear meaning in almost every context it appears in. But in physics, in the specific physics of energy density, of how much energy occupies a given region of space, the number less than 0 becomes something that resists casual acceptance. Not because the mathematics disallows it. The mathematics, as it turns out, is entirely comfortable producing it. But because the physical meaning of negative energy density is not simply less energy than usual. It is something categorically different from that. Something the universe, operating under its ordinary rules with its ordinary matter, declines to produce in any quantity that would be useful. Energy density is a measure of how much energy is packed into a volume of space. Matter has positive energy density. Mass is energy, as the famous equation implies, and every particle of ordinary matter contributes positively to the energy content of whatever region it occupies. Photons contribute positively. Heat contributes positively. Even the quantum vacuum, the baseline state of empty space stripped of all particles and radiation, has an energy associated with it, the result of quantum fluctuations that cannot be entirely suppressed no matter how thoroughly you evacuate a region. Negative energy density would mean that the energy contribution of something to a region of space is, in the accounting general relativity uses, below the vacuum baseline. Below nothing. Not just low, genuinely, measurably subtractive. This is not the same as cold, not the same as dark, not the same as empty or quiet or absent in the ordinary sense. Cold is low thermal energy, which is still positive. Dark is low electromagnetic energy, which is still positive. Vacuum is low everything, which is still technically positive. Negative energy density is none of these things. It is a specific physical condition with no everyday analogue, which is part of why explaining it tends to produce more confusion than clarity the faster it's delivered. Negative energy is, and I recognize this is a strange thing to say about a physical property, deeply uncooperative, not in the sense that it resists detection or defies measurement, in the sense that every time you approach the question of where to find it or how to produce it, or whether it exists in forms that matter for the wormhole problem, it offers something just small enough to be interesting and just insufficient to be useful. The Casimir effect is the example that arrives here, as it always does. 2 metal plates, placed parallel to each other, separated by a gap of nanometers, in a vacuum that has been evacuated as completely as possible. Under these conditions, the plates experience an attractive force. They pull toward each other, measurably, in a way that cannot be explained by electromagnetic attraction because the plates are uncharged. The explanation comes from quantum field theory. The space between the plates is too narrow to support all the wavelengths of quantum vacuum fluctuation that exist in the space outside. So the outside has more zero-point energy than the inside, and the difference produces a pressure that pushes the plates together. The energy between the plates, in this configuration, is negative relative to the vacuum outside. This is real. It has been measured. It is one of the most carefully confirmed predictions of quantum electrodynamics, and it is not controversial in any corner of physics that engages with it seriously. So negative energy density exists. The Casimir effect demonstrates that. If you find yourself drawn to sitting with ideas like this one, the kind that open rather than resolve, the Patreon for this channel is a place where that kind of thinking gets to go a little further. What the Casimir effect does not demonstrate is that negative energy density can be produced at scales, densities, or geometries relevant to holding a wormhole throat open. The numbers involved are almost offensive in their inadequacy, not as a criticism of the effect itself, which is a genuine and important piece of physics, but as a comment on the ratio between what the Casimir effect provides and what Morris-Thorne calculations suggest a traversable wormhole would require. The negative energy between Casimir plates is real, and it is also extraordinarily dilute, relevant only across distances measured in nanometers, requiring materials and conditions that have no natural analogue in the universe's ordinary behaviour. Scaling from Casimir to wormhole is not a matter of building bigger plates or finding a more efficient configuration. The relationship between the geometry of the effect and the geometry of a macroscopic wormhole throat is not the relationship between a small version and a large version of the same thing. They are structurally different problems that share a concept in negative energy density, without sharing a physical mechanism that connects them. This is the part that sitting with it long enough starts to feel less like a technical limitation and more like the universe making a specific and considered point. There have been proposals, squeezed states of light, quantum optical configurations in which the uncertainty in one physical property is reduced below the vacuum level with a corresponding negative energy contribution. Certain configurations of quantum fields in curved spacetime, modifications to the standard model that might permit stable negative energy distributions at macroscopic scales. Though these modifications are speculative in ways that require careful handling before they can be presented as anything approaching serious candidates. What all of these share is the same fundamental problem the Casimir effect has. The quantities are wrong. The magnitudes of negative energy density that quantum field theory permits, and the constraints on how much negative energy can exist, how long it can persist, how it relates to the positive energy that must accompany it in any physically consistent configuration, appear to fall short of what general relativity requires at the wormhole throat by a gap that has not been closed by any proposal that survives contact with both sets of equations simultaneously. The constraint is sometimes called the quantum inequalities, a set of bounds derived from quantum field theory that limit how much negative energy can exist in a given region over a given time. These bounds are not arbitrary. They arise from the same framework that produces the Casimir effect in the first place, and they are, for the wormhole problem, grimly restrictive. There is a way of thinking about this that is not quite despair and not quite optimism, and sits somewhere in between those, in a place that has no good name. Negative energy exists. The universe produces it in small quantities under specific conditions, in ways that have been measured and confirmed and built into the theoretical framework with enough precision that it would be strange to dismiss it. The concept is not exotic in the sense of being invented to solve a specific problem. It arises naturally from quantum field theory, independently of any wormhole discussion, and would be part of physics even if wormholes had never been theorized. The question is whether exists in small quantities under specific conditions and exists in the quantities and configurations that a traversable wormhole requires are separated by an unbridgeable gap or merely a very large one. That question does not have a confirmed answer, not a negative one. Nobody has proven that the required exotic matter cannot exist, that no physical process could produce it, that the gap is fundamental rather than merely enormous, and not a positive one either, for the same reason that none of the proposals have produced what the equations ask for. It is a question that sits unresolved in the sit of space between what quantum field theory permits in principle and what general relativity requires in practice, and whether those two frameworks, which are not yet fully reconciled with each other anyway, will eventually agree on an answer that makes traversable wormholes physically coherent, or whether the answer has been no all along. We simply don't yet have the mathematics to see it clearly. Something less than zero, real enough to measure, not yet enough to matter. Every telescope we have ever built has not seen one. This is worth saying plainly before anything else, because the conversation around wormholes can accumulate so much theoretical texture, the geometry, the exotic matter, the energy conditions, the modified gravity proposals, that the observational situation starts to feel like a detail rather than the central fact. It is the central fact. Decades of looking, with instruments of increasing precision and sensitivity, aimed at the regions of the universe most likely to harbour the extreme gravitational conditions that wormhole formation might require. And the result is consistent. Nothing that demands a wormhole to explain it. Not nothing surprising. The universe has been generous with surprises. Gravitational waves, the accelerating expansion, the shadow of a black hole photographed for the first time in 2019. It has repeatedly produced phenomena that required new physics to understand. Phenomena that were not predicted by prior observation, and that changed the shape of what physics expected to find next. Wormholes are not among them. The search has not been passive. Physicists have described in detail what signatures a macroscopic wormhole might produce if it existed, what distortions it would create in the light passing near it, what effects it would have on the orbits of nearby objects, what fingerprints it might leave in the gravitational wave data that detectors like LIGO and Virgo have been accumulating since 2015. These are not vague predictions. They are specific enough to be useful, which means specific enough to be tested, which means specific enough to produce a result when the right data is examined. The results have not been confirmations. Gravitational lensing is the most intuitive detection method and the one that has been applied across the widest range of observations. Mass bends light. This is a confirmed prediction of general relativity, observed since Eddington's 1919 solar eclipse measurements and refined continuously since. Any sufficiently massive or geometrically unusual object between a light source and an observer will distort the apparent position, brightness, and shape of the source in characteristic ways. Black holes produce lensing signatures. Neutron stars produce them. Even ordinary stars, when they pass in front of background sources, produce measurable lensing effects through a process called microlensing. A wormhole mouth, a region where space-time is dramatically curved, connecting to a distant region through a throat, would produce lensing. But the pattern would differ from a black hole's pattern in ways that should, in principle, be distinguishable. The light bending around a wormhole would include contributions from both the gravitational mass of the structure and from the geometry of the throat itself, which has no equivalent in a black hole. there might be additional images or characteristic brightness patterns or specific distortions in the ring of light that forms when a source is almost perfectly aligned with a compact object. No such distinctive pattern has been found, not in microlensing surveys, not in the imaging of Sagittarius A star, the supermassive object at the centre of the Milky Way, which is one of the candidate locations for wormhole detection that has been examined most carefully. Not in any of the galaxy centres that have been studied in enough resolution to make the comparison meaningful. Stellar orbits offered a different angle. The star S2, a well-studied star orbiting Sagittarius A star on a path that takes roughly 16 years to complete, has been tracked with extraordinary precision since the 1990s. Its orbit has been used to confirm the mass of Sagittarius A star, to test general relativity and strong gravitational fields, and to map the space-time geometry in the immediate vicinity of the galactic centre with a level of detail that was not available to any previous generation of astronomers. If a wormhole were present at or near Sagittarius A star, its gravitational influence on S2's orbit would introduce perturbations, small deviations from the path predicted by a standard black hole model. A paper published in Physical Review D proposed that examining S2's orbit for exactly these perturbations could, in principle, reveal or rule out a wormhole. The precision required to detect them is, and this is said without exaggeration, at the edge of what current instrumentation can achieve and possibly beyond it. The examination has begun. The data from S2 does not currently require a wormhole to explain it. Whether the precision available is yet sufficient to definitively rule one out is a different question, and the answer carefully given is, not quite, not yet. The method is sound, the data is accumulating, and the conclusion is still pending, in the way that careful observational science is often pending. Not done, not confirmed, not refuted. Gravitational wave detectors introduced a third approach, and it is the most recently developed of the three. When two black holes merge, they produce a characteristic gravitational wave signal, a chirp, in the language of the field, a specific pattern of increasing frequency and amplitude that matches what general relativity predicts for the inspiral and coalescence of two compact objects. LIGO detected this pattern for the first time in September 2015, and the detection has since been repeated dozens of times, with neutron stars added to the catalogue of confirmed sources. A wormhole merger, or the perturbation of a wormhole by a nearby massive object, would produce gravitational wave signatures with a different character. The quasi-normal modes, the specific frequencies at which the spacetime rings after a perturbation, would carry information about the geometry of the source. A wormhole's quasi-normal spectrum differs from a black hole's in ways that depend on the throat geometry, the presence of exotic matter, and other structural details. In principle, a sufficiently sensitive detector examining the sufficiently clear signal could distinguish them. In practice, no gravitational wave event detected so far has required a wormhole interpretation. Every signal in the catalogue is consistent, within the current measurement precision, with the standard black hole or neutron star models. This is not a refutation, it is an absence, and absence has its own, well, it has a texture that is different from a refutation, though the difference is sometimes harder to hold on to than it should be. In January 2026, a paper published in Classical and Quantum Gravity, co-authored by researchers at the University of Portsmouth, arrived at a conclusion that was careful in its phrasing and somewhat grimmer in its implication. The paper, which revisited the original Einstein-Rosen bridge and its relationship to the broader concept of traversable wormholes, noted that there is no observational evidence for macroscopic wormholes and no compelling theoretical reason, within standard general relativity, to expect them. The phrasing "no compelling theoretical reason to expect them" is worth sitting with for a moment, because it goes slightly further than simply saying they haven't been found. It suggests that the absence is not just an observational gap, not just a matter of looking in the wrong places with insufficiently sensitive instruments, but is at least partially consistent with what the underlying theory, taken seriously and without modification, would lead you to predict. This is not a proof of non-existence. Physics does not work that way, and the paper does not claim otherwise. What it is an honest accounting of where the theoretical motivation stands alongside the observational record, thin on both counts, related to each other in a way that is not encouraging, while remaining genuinely open in the sense that no definitive door has been closed. There is a quality to sustained absence that is different from a single negative result. One null result in a search can be a matter of timing or location or instrumental sensitivity. 10 null results across different methods and different targets begin to describe something. Not a proof, the word a proof belongs to mathematics, not to observation, but a profile. The profile of a phenomenon that, if it exists at macroscopic scales accessible to our instruments, has so far declined to announce itself in any of the ways it would be expected to. Declined is the wrong word. The universe doesn't decline anything. It simply is what it is, and what it is, from the perspective of wormhole detection, is quiet. There are astrophysicists who take the search seriously, who publish on the detection methods, who would argue that the sensitivity required to make a definitive statement hasn't been reached yet, and who are right to argue this. The instruments will improve. Gaia's continued mapping of stellar positions and motions will refine the orbital data. Next-generation gravitational wave detectors will increase sensitivity across frequency ranges that current instruments cannot fully access. The search is not over. But the current state of it, the accumulated weight of decades of observation across multiple independent methods, pointed at the most promising candidate locations, using the best instruments humanity has yet constructed, is this: nothing found. Nothing that requires a wormhole to explain it. Nothing that even strongly suggests one. The universe has been looked at carefully, for a long time, by people who knew what they were looking for. So far, it has not looked back. Outside somewhere it has gone properly dark. Not the preliminary dark of early evening, when there's still a bruised edge of light along the horizon, and the sky is more blue-grey than black. The real dark, the kind that arrives without announcement, that you only notice when you look up and realise the transition already happened, that the stars have been out for a while, and you weren't paying attention to the moment they appeared. That's where this chapter lives. In the part of the night where the earlier thinking has had time to settle, where the facts are not new anymore but have taken on a different weight. The weight things get when they've been sitting in the mind long enough to stop feeling like information and start feeling like something closer to understanding. The distance to Andromeda is 2.5 million light years. This is the same fact it was at the beginning, but it sits differently now. Here is the thing about the distance, the correction worth making quietly without drama. The distance is not actually the problem. 2.5 million light years sounds like the problem. It is the first obstacle named, the number that makes the endeavour seem immediately hopeless, the measurement that stops most conversations about intergalactic travel before they properly begin. But distance in physics is a more pliable concept than it appears. General relativity describes a universe in which space is not a fixed, rigid backdrop. It is a structure with geometry, and geometry can, under the right conditions, be arranged differently than the straightforward this far from that reading of a ruler would suggest. Time dilation demonstrated one version of this pliability. Not a shortening of the distance, but a compression of the time required to experience crossing it, a concession the universe makes to objects moving fast enough, allowing subjective journeys of decades where objective ones would take millions of years. The distance remains, the experience of it changes. That is not nothing, even if it is not enough. The wormhole concept offers a more radical version of the same underlying idea, not compressing the experience of crossing a fixed distance, but connecting two distant points through a path whose length through the wormhole geometry is far shorter than its length through ordinary space. The distance measured through the shortcut could, in principle, be traversable in days or hours. The distance measured the long way around through the space between here and Andromeda, across 2.5 million light-years of ordinary geometry, remains what it is. Both are real. Both are simultaneously true in a universe whose space-time can fold. The distance is not the problem. The structure of space-time is not the problem either. The structure, as it turns out, permits this in the mathematical sense. The problem is what you would need to put inside the fold to keep it from closing. And that problem is not a distance problem. It is a material problem, a deeply unsolved one. This distinction matters more than it might initially seem. There is a version of hopelessness that comes from confronting a fixed, immovable limit, the kind of limit that says this cannot be done because the universe forbids it at the most fundamental level. Special relativity and the light barrier have something of this quality. The requirement of infinite energy to reach light speed is not a technological hurdle, but a structural feature of the relationship between mass and velocity, and no engineering, however advanced, changes that relationship. The wormhole problem does not have exactly this character. What it has is harder to name, something between an unsolved problem and a possibly insoluble one, sitting in the space where the physics is incomplete, where quantum gravity has not yet been worked out fully enough to give a final answer, where the energy conditions that general relativity imposes might or might not be relaxed by effects that only become visible at the Planck scale. The door is not confirmed to be locked. It is confirmed to require a key that has not been found, whose existence has not been confirmed, whose shape can be described mathematically, but whose material reality remains entirely open. That is, and I want to be careful here, because this could sound like optimism performing as analysis, genuinely different from impossible. Not comfortably different. Not different in a way that suggests the answer is coming soon, but different in a way that is physically meaningful. That is why serious physicists continue to publish on traversable wormholes rather than simply noting the problem and moving on. The exotic matter requirement, revisited from here, looks slightly different than it did when it first arrived. When it first appeared, it arrived as an obstacle, the thing the throat needs that the universe declines to provide at scale, and that framing is accurate. But there is another way to hold it, one that takes longer to arrive at and sits more honestly with the full picture. The exotic matter requirement is also a precise description. It tells you with mathematical specificity exactly what would need to exist for the problem to be solvable. Not a vague, we need better technology, or we need more energy. A specific set of physical properties, a specific relationship between energy density and pressure, a specific violation of a specific energy condition in a specific region of space-time. The requirement is demanding, but it is also, and this is the part that takes a moment to register, extremely precise. Precision is not nothing. Precision means the question is well formed enough to be answered, if an answer exists. Whether the universe contains anything that satisfies those precise requirements, anywhere, under any conditions, is the open question. Not whether the requirements are coherent. They are coherent. The equations say clearly what is needed. The question is whether physics, fully understood, including the quantum gravitational regime that general relativity cannot access, produces it somewhere. Space-time, considered as a medium, is, and this is the irrational observation arriving now, the one that doesn't belong in a physics paper but belongs here, quietly, constitutionally indifferent to urgency. It does not accommodate desire. It does not bend for need. It is what it is with a thoroughness that makes other kinds of intransigence seem almost negotiable by comparison. The curvature responds to mass and energy according to rules that do not contain an exception clause for species that have developed the cognitive equipment to understand those rules and wish they were otherwise. There is something clarifying about this, if you let it be clarifying rather than discouraging. Understanding a limit precisely is not the same as accepting defeat. These are different activities with different implications. Accepting defeat involves turning away from a problem, concluding that further engagement is pointless, redirecting resources and attention elsewhere permanently. Understanding a limit precisely involves knowing exactly where you are standing, what is in front of you, what it would take to change the situation, and what remains genuinely unknown about whether that change is available. It is a more honest and more useful position than either false optimism or premature resignation. The limit in front of the Andromeda question is understood with considerable precision. The distance is known. The geometry that would circumvent it is mathematically described. The material requirements are derived. The observational record is clear. The unsolved portions are identified. Exotic matter, quantum gravity, the reconciliation of two frameworks that are not yet fully unified. None of this is vague. All of it is, in the scientific sense, well characterized. What is not characterized, what remains genuinely structurally open, is whether the unsolved portions have solutions that the universe is willing to provide. Time dilation appears here one more time, briefly from a different angle than before. When it first appeared in this conversation, it arrived as a loophole. The universe's strange lopsided concession to high-speed travel, compressing the traveller's experience while leaving everything else to age normally. It was presented honestly, generous in one direction, severing in every other. A gift that arrives with a cost most people wouldn't accept. From here, it looks like something slightly different. It looks like evidence that the universe's geometry is more flexible than it first appears. Not flexible in the ways we want, not flexible on the schedule we'd prefer, but flexible in the sense of containing more degrees of freedom than Newtonian physics suggested. Time dilation was not predicted by everyday experience. It was not intuitive. It arrived from the mathematics and then was found, to everyone's slight amazement, to be physically real, measurable in atomic clocks aboard aircraft, built into the operating assumptions of GPS satellites, confirmed in particle accelerators where muons created in the upper atmosphere survive long enough to reach the ground, because their internal clocks, running fast, tick slowly relative to ours. The universe surprised us with this. It may, not certainly, not probably in any quantified sense, but genuinely may, contain other surprises of the same character. Properties of geometry and energy that are not intuitive, not predicted by everyday experience, not visible from where we currently stand in the development of physics, but real in the same way that time dilation turned out to be real. This is not a promise. It is an observation about the track record of the universe when examined carefully. The question of Andromeda, held here in the late part of the night, does not resolve. It was never going to resolve in a single conversation, or a single video, or a single era of physics. It is the kind of question that requires the full machinery of a not yet complete understanding of how space-time and quantum mechanics fit together. A reconciliation that is one of the deepest unsolved problems in physics, one that the best minds in the field have been working on for decades without arriving at a final answer. What has happened here over the course of these chapters is something different from resolution, something more like the question has been located, not answered, but placed. Its dimensions have been walked, its edges found, the places where it is well understood, and the places where it is not have been roughly mapped. 2.5 million light years, a geometry that permits connection in principle, a material requirement that has not been met, an observational record that has found nothing, a set of open questions at the frontier of physics that might or might not change the picture. That is where the problem lives. Not in hopelessness, not in easy optimism, but in the honest, slightly uncomfortable territory between them, where the universe has not said yes and has not said no, where the mathematics contains the possibility and the physics has not confirmed it, where the distance is real, and the structure that might bridge it is real, and the thing that would hold it open is, as yet, nowhere to be found. The dark outside is the same dark it was when this chapter started. Andromeda is in it somewhere, faint, ancient, arriving continuously at the eye of anyone patient enough to look, still there, still unreachable, still in some quiet and unresolved sense worth thinking about. There is a particular quality at the end of a long thought. Not the end of a conclusion, this is not that, and it would be dishonest to frame it that way. More like the end of a sustained attention, the moment when you have been looking at something carefully for long enough that the looking itself becomes noticeable. The eye that has been trained on a distant object begins to be aware of itself as an eye. The mind that has been moving through a problem begins to feel the movement. Something in the quality of the attention shifts, not losing interest, but arriving at a different kind of interest, wider, less focused, still present, but breathing differently. That is where this chapter lives. The question of Andromeda was never, underneath all the physics, really about Andromeda. This takes a while to become clear, and it doesn't fully become clear even now. But there is something in the accumulated weight of everything that has been covered here. The distances and the geometry and the exotic matter and the decades of observational silence that starts to point somewhere beyond the specific galaxy 2.5 million light years away. The question was always partly about something more persistent, something that predates telescopes and general relativity, and the Kardashev scale and every framework that has been used to approach it. It is the oldest question about space, really. Not what is out there, though that is part of it. More specifically, can we go? The desire to close a distance that feels, for reasons not entirely rational, like it should be closable. The stubborn intuition that visibility implies reachability, that if something can be seen, it ought to be approachable, that the universe should not be organized in a way that shows you something and then builds an absolute wall between you and it. The universe is, in fact, organized that way. For now, with what is currently understood, for us at this particular moment in the development of physics and engineering and civilization, the wall is real, not necessarily permanent, that word is doing more work than the evidence supports, but real and high, and made of material the equations have described and physics has not yet provided. What remains open is not nothing. The physicists who still publish on traversable wormholes are not, by and large, people who believe the solution is around the corner. They are people doing what physics asks, following the mathematics where it leads, testing the boundary conditions of what the theory permits, looking for the places where two frameworks, general relativity and quantum mechanics, might, when properly reconciled, produce answers that neither framework produces alone. This work is slow and frequently inconclusive and occasionally produces a result that looks promising and then doesn't survive contact with the next set of constraints. It continues anyway, not from stubbornness exactly, though there is a kind of intellectual stubbornness in good theoretical physics that is hard to distinguish from patience. It continues because the question is well-formed enough to be worth working on, because the universe has surprised physics before with answers that weren't visible from the previous position, and because the alternative, deciding in advance that the open questions are permanently closed, is not how the discipline functions. If this is the kind of thinking you want to go further with, the Patreon for this channel is where those conversations continue. The link is in the description. There is a specific thing that happens when you look at Andromeda, not with a telescope, with your eyes, on a clear night, far enough from the light of cities that the sky has recovered some of its original depth. You have to know where to look, roughly, just off the constellation Andromeda itself, which is itself off the Great Square of Pegasus, which is a reasonable landmark if the sky is dark enough for it to be obvious. You look at the general area and you let your eyes relax, not staring directly but slightly to the side of where the galaxy should be, using peripheral vision the way experienced observers do, because the rod cells at the edge of the retina are more sensitive to faint light than the cone-dense center. And then it's there, a smudge, elongated very slightly, barely distinguishable from a cloud except there are no clouds tonight, faint enough that attention sharpens it and over-attention makes it disappear, a thumbprint of the sunlight on the dark. What is actually happening at the level of physics? Photons that left the Andromeda galaxy 2.5 million years ago, that have been travelling through intergalactic space since before Homo sapiens existed as a species, are completing their journey by landing on the retinal cells at the back of your eye and triggering a cascade of electrochemical signals that your visual cortex assembles into the experience of seeing a faint, slightly fuzzy patch of light slightly north of the star Merak. The light is, I want to say patient, which is wrong because photons don't wait for anything. But there is something in the sheer duration of the crossing that has a quality patience would describe if patience were a property of physics rather than of minds. 2.5 million years. The light carries no memory of its origin. It doesn't know it left a galaxy, doesn't know it crossed intergalactic space, doesn't know it arrived. It just arrives the way photons arrive, completing a path determined by the geometry of the space it moved through, indifferent to the distance it covered. You see it. Your brain assembles it. Something in you recognizes that the thing you are looking at is very far away, not with the felt weight that the number actually deserves, because that weight is not available to the perceptual system, but with the thready, intellectual version of distance that comes from knowing rather than sensing. This gap between knowing the distance and feeling it is perhaps the most honest summary of everything this conversation has been circling. The universe is not organized at human scale. It does not present itself in units the body can verify. It offers the light and the mathematics that describes where the light came from and how long it took, and then leaves the understanding of both to a cognitive apparatus that was shaped by pressures having nothing to do with intergalactic distances. We do surprisingly well given that. Surprisingly well at following the math into the territory the intuition can't reach, at building instruments that extend the senses into regimes the body never evolved for, at sitting with a fact like 2.5 million light years and extracting from it slowly what it actually implies about geometry and matter and the structure of space-time. This particular conversation ends here, but the question doesn't. It keeps going in the papers that get published, in the instruments that get refined, in the slow accumulation of observational data, that will eventually either find something or make the absence more precisely characterized than it currently is. It keeps going in the way that good physics questions keep going, not toward a predetermined answer, but toward whatever the universe actually contains, which has so far been stranger and more various than any prior expectation. Somewhere in that ongoing work, there may be an answer to the wormhole question, whether exotic matter in the required quantities is physically realizable, whether the quantum gravitational regime produces effects that relax the energy conditions general relativity imposes, whether the silence in the observational record reflects genuine absence or merely insufficient sensitivity. These are not rhetorical questions. They are open ones, being worked on by people with the mathematical equipment to work on them, in a discipline that has a reasonable track record of eventually finding what it's looking for, or finding something better. The gratitude that belongs at the end of something like this is not a formality. Matthew M. and Brian Winter, whose support as co-creators of this work makes the depth of it possible, thank you. Alison, who's been here the longest, whose presence at the beginning of this channel is woven into whatever this has become, thank you genuinely. And everyone else on Patreon who has decided this kind of quiet, careful thinking about large questions is worth sustaining. This exists because of that decision, and it is not taken lightly. Andromeda is still out there. If the night is clear enough where you are, and the sky dark enough, it is visible right now, has been this whole time sitting in the same patch of sky it always occupies from Earth's perspective, moving imperceptibly closer at a rate that will take billions of years to matter, sending light that left long before you were born and will continue arriving long after. It cannot be reached. Not tonight. Not with anything that currently exists or is currently understood. The geometry that might connect here to there remains theoretical. The material that might hold that geometry open remains unconfirmed, and the observational record has returned consistently the same answer. But it is seen. Every clear night, by anyone patient enough to find it, the light arrives. Ancient, unhurried, carrying no information about whether the crossing is possible, just the fact of having crossed, the 2.5 million year fact of it, landing quietly in the eye of whoever happens to be looking. That's not nothing. It might even be for tonight enough.